So, so let me first conclude what I started yesterday, namely a proof of property T for SL3R. And so yesterday I defined this relative T property. So to remember the definition, so G is always locally compact group. And so H is a closed subgroup. And we say that the pair GH has relative T. If for every representation pi almost having invariant vectors, pi restricted to H has invariant vectors. And okay, so I will need two propositions. The first one is the fact that the pair consisting of the semi-direct product R2 with SL2R has relative T with respect to the normal subgroup R2. So this has relative T. And so this is due to Kazhdan. The second proposition actually goes back to Mortner in the 50s. And it's a property of representations of SL2R. And it says the following. Take the unipotent subgroup, upper unipotent subgroup in SL2R. And let pi be a unitary representation of SL2R. And psi in the Hilbert space, a pi n fixed vector. So you assume that you have a vector which is fixed under that subgroup. Then actually that this vector is fixed under the whole of SL2R. And the fact that the representation is unitary is absolutely crucial. For instance, this is something, so here, unitary is important. This is something which is false, for instance, for finite dimensional representations of SL2R, but these are non-unitary. And okay, assuming these two propositions, so let me give a proof of property T for SL3R based on proposition 1 and 2. So, okay, let pi be a representation of SL3R, almost having invariant vectors. And first, we embed the semi-direct product of proposition 1 into SL3R as follows. So here, a group element consists of is a pair consisting of a vector in R2 and a 2 by 2 matrix. So it's a pair XA, and we map it to AX01. Pardon me? Yeah, the SL2R is acting linearly. SL2R is acting linearly on R2. And okay, so well, let me give a name. Let me give a name to the image of R2 under that embedding. So let me call it V. And if we take the representation pi and restrict it to, well, first to the image of this symmetric product and then to V, we see because of the relative property T for, well, because of proposition 1, that we will have a non-zero V invariant vector. So by proposition 1, find psi in H pi, non-zero pi V invariant vector. And now the goal is to show that psi is actually fixed under the whole of SL3R. And to do that, we embed SL2R in two other ways. In SL3R, the first is like this, and the other one is by putting SL2R in the lower right corner. So it's 1, 0, 0. So like that. And you see that for the first embedding, the element in the upper right corner corresponds to the group N in proposition 2. For the second embedding, the element in position 2, 3, that one, corresponds to the subgroup N for the third embedding. So, by proposition 2, psi is fixed by the images of these two embeddings. But together, these two embeddings generate a SL3R. End of the game. So these two embeddings generate SL3R. And so, okay, so we are left to prove these two propositions. And okay, let me do that. Okay, proof of proposition 1. And okay, so property T has been around for, well, since 1967. And there have been many improvements, many new proofs. But this is something, this is something which basically, this is the core part of the proof. I mean, something which has not, I mean, there has been shortcuts, But this part of the proof has never been modified, and she's there. So it's in, and the point is, as you will see, this is something we're going to use the spectral theorem. And this means that this is something which really pertains to the realm of Hilbert spaces. So, and this makes property T very, very hard to extend to other Banach spaces, for instance. And a number of people, starting with Fisher and Margulis, ask whether there are versions of property T for group actions or more general Banach spaces. And they succeeded in doing something for LP spaces, basically by reducing to the L2 case, using some trick. But for more general Banach spaces, there is basically nothing. And my opinion is that it's really due to the fact that we cannot bypass the use of the, we are unable to bypass the use of the spectral theorem. So, indeed. So first let pi be a unitary representation of that semi-direct product. Then when we restrict to the normal subgroup R2, well, we restrict to an abelian group. So that measure, that representation has a so-called spectral measure. A spectral measure which is defined on the dual group, R2 hat, well, that we shouldn't identify with R2, at least not canonically. So as a spectral measure on the dual R2 hat, and that is, that's a projection valued measure on Borel subsets B of R2 hat, such that when we take a group element xy that in R2, we'll be able to write something like this. Pi of xy will be the integral over R2 hat of e to the 2 pi I lambda x plus mu y dE of lambda mu. Yeah? It's the unitary dual, or it's the dual vector space, as you get. It's the same. But it's not R2. Pardon me? Yeah, but you see, if you measure x and y in seconds, you measure lambda and mu in hertz. So it's not the same. They are isomorphic, but not canonically. Okay, so so it's really either the Pontryagin dual or the dual vector space. That this I can buy, but I cannot buy that is the same as R2. So remember how does it go? This projection valued measure. So for every Borel subset B, we associate E of B, which is a projection, a projector operator, a projection on the Hilbert space of pi. And okay, and this measure satisfies this relation, which makes sense in the weak sense precisely. And moreover, if we remember that pi is actually a representation not only of R2, but on the whole semi-direct product, we see that this spectral measure satisfies some equivalence relation. So, namely, it satisfies the following, that if we apply an element of SL2R, and if we move the Borel set by that element, maybe we are on the dual, so maybe okay. I shouldn't I shouldn't be caught in my own trick. So let me put a transpose here. So this will be pi of g, E of B, pi of g inverse. Now, as I said, if you are not happy with projection valued measure, you can turn that into honest probability measures on R2 hat in the following way. So whenever you pick psi, a vector in your Hilbert space of norm 1, then you may define mu sub psi of B as EB psi psi, and this is an ordinary probability measure. On R2 hat, and which will satisfy the following relation, that if you take the coefficient of the representation associated with the vector psi, this will be the integral over R2 hat of e to the 2 pi I lambda x plus mu y d mu psi of lambda mu, which means that the coefficient is exactly the Fourier transform of that measure, Fourier transform in the usual sense. Okay, using the equivalence relation, which is down there, you have that if you take G in SL2R, and if you push forward that probability measure by the action of G, you get exactly the measure associated to pi sub G of psi. And now let's make a small computation. So let us estimate the distance, well, the so-called total variation distance between mu sub psi and mu pi of g psi. So you pick a Borel set, well, in R2 hat, and you compare the values of these probability measures on B. So mu psi minus mu pi of G psi of B. Okay, so this is E of B psi minus E of B pi of G psi of G psi. And now, okay, usual trick, I'm going to subtract and add the same quantity to be able to apply Cauchy-Schwarz in a clever way. So let's see. This will be EB psi scalar product with psi minus pi of G psi. So minus no, plus EB psi minus pi of G psi scalar product with pi of G psi. And I think that even the signs are correct. Maybe there's some parentheses like that. Yeah. And so here, so we apply twice Cauchy-Schwarz, so to the effect that this is less than twice the distance between psi and pi of G psi. Okay. So assume that psi n. So now I'm going to assume that pi almost has invariant vectors. So assume that psi n is a sequence of unit vectors such that the function g goes to pi of G psi n minus psi n goes to, well, this sequence of functions goes to 0 for n going to infinity, uniformly on compact subsets. I want to show that in restriction to R2, pi has non-zero invariant vector. So assume it's not the case. So assume by contradiction that pi restricted to R2 has no invariant vectors. How does it translate in terms of the spectral measure? Well, the projection on the R2 invariant vector is E of 0, 0. 0, 0 corresponds to the trivial character, and having invariant vectors means that when you project to the trivial character, you get something non-zero. So here my assumption translates into E of, let's say, of the singleton 0, 0, this is 0. So I consider this sequence of probability measures, mu sub psi n. Mu sub psi n can be seen as a probability measure on R2 hat minus 0, 0. Okay. And so what this means, what the estimate that we made here means that we have a sequence of probability measures which are more and more invariant. I mean, which are asymptotically invariant. We would like to, for instance, to take a fix, to extract a fixed point, a fixed limit point. We cannot, because R2 minus 0 is, or R2 is not compact. But there is a trick to go around the difficulty, which is to project to the projective line. So we push our measures to the projective line, which is compact. So push the nu psi n to a sequence of probability measures on the projective line associated with R2 hat. And we can do that only because we have the assumption that these measures do not charge 0. If they were an atom at 0, we could not do that. But here we can. And of course, the projection from R2 minus 0 to the projective line is SL2R equivariant. And so we get well, okay, this sequence is asymptotically invariant under SL2R. You can pull back functions, you can push forward measures. Yeah, yes, exactly. Mm-hmm. So that's, yeah, maybe I should have said push forward. So so by compactness, a limit point is that would be an SL2R invariant proba measure on the projective line and that's a contradiction because this is something which does not exist. Yeah. So as I said, this was really the core of the proof. And now it remains to prove this proposition 2 of Mortner. That's much easier. I think you will like it. It's rather fun. There is a geometric argument. So proof of proposition 2. So remember the framework. We have psi. Okay. Remember that we are n is the upper unipotent subgroup in SL2R. And we have psi in the Hilbert space of representation of SL2R, a pi n fixed vector. So, introduce two more subgroups. First, the diagonal subgroup. And then the lower unipotent And okay, together, these three subgroups generate SL2R, right? And if we prove that psi is also fixed by diagonal subgroup, then it will also be fixed by n minus because of Mortner's lemma of yesterday. Indeed, that matrix, when you conjugate by a diagonal matrix, you can let, if you let t go to plus or minus infinity, you can tend to the identity. So that matrix has the identity in the closure of its conjugacy class. So by Mortner's lemma, psi is pi of n minus fixed, and together n, a, and n minus generate SL2R. Okay, so we really have to show that psi is A fixed. And to do that, we consider the function phi of g, which is pi of g psi scalar product with psi. So as a function on SL2R. And the first remark, which is that this function is by n invariant. Namely, that if we multiply on the left by some element of n and on the right by another element of n, so if we consider phi of n, g, n prime, this is phi of g. So for every n and n prime in the upper unipotent. Why is it? Well, on the right, it's because the n will be absorbed by psi, because psi is n fixed. And on the left, you move the n prime to the other side, and then it is absorbed by psi, because psi is n prime fixed. Okay. So, so using the fact that this function phi is right and invariant, we have that phi descends to a function on SL2R modulo n. But what is SL2R modulo n? It's R2 minus the origin. Because n is exactly the stabilizer of the first basis vector. So, and this is an equivalent homomorphism for the left action of SL2R. So this is SL2R equivariant. Now let me make a drawing. And since I do have colored chalk, let me even use it. So I take away the origin. And what are the orbits of n on R2 minus 0, minus the origin? Well, on the horizontal axis, these are the points. But away, these are the horizontal lines. And now left n invariant means that our function is constant on all of the horizontal lines. So phi constant on each of these lines. Also, we have the first basis vector, 1, 0. And we know what is the value of phi at this point? Well, it's the value of phi at the identity, so it's 1. So phi is 1 here. But now, what can be the values of phi on the horizontal axis? Well, it has to be 1 because phi is continuous. So when you let a yellow line go to the horizontal axis, by continuity and the fact that phi is constant, you see, okay, yeah, but that's a nice and roundabout way of proving that phi is constant on the original axis. Yeah, so by continuity, phi is 1 on the horizontal axis. And if you take the positive horizontal axis, this is exactly the orbit of 1, 0 under A. And so we get that phi of, let's say, if I call this diagonal matrix A sub t, phi of A sub t is 1. So this means that pi of A sub t, psi is psi. And again, by the equality case of Cauchy-Schwarz, we are finished. So pi of A sub t, psi is psi. By the equality case of Cauchy-Schwarz. Okay. So basically what I did so far was explain to you in fairly details the 3-page paper by Kazhdan. Which one? Sorry.
In proposition 2,
you
have the subgroup n, and
yeah.
fixed vector implies fixed by SL2. And is there any similar result for SL3? Or here you have 4 cycle flows and
yeah. Okay. Yeah, I think this has been looked at. I don't have any reference on to give you like that, but yeah, I'm sure that this has been looked at.
It doesn't help for the whole project because it's just the
yeah, because yeah, the point is that at some point you must have an existence result for a fixed vector, and once you have it, you are in business. So and that's the whole point of proposition 1. So let me change a little bit the order of the presentation, and I think that to address a question which was asked to me yesterday, let me talk immediately about one of the main applications of property T, and this is the construction of so-called expander graphs. So it's an application in graph theory. And so we will change subjects fairly drastically. And so first let me motivate the question. So the question expanders appeared in the 1960s, coming from the community in a communication system. So people who, well, let's say engineers who want to design efficient communication system, and well, it's a natural idea to try to model these communication systems by graphs. So suppose we want to use finite graphs, X, and for me a graph consists of a pair of vertices, a set of vertices, V, and a set of edges, E. So V stands for vertices, and E stands for edges. So we want to use finite graphs to model good communication systems. Oh, by the way, I think that the engineers would talk about nodes rather than vertices, but that's the same thing. And where the information propagates along edges, say in one unit of time. So for every unit of so at the beginning, at time 0, some vertices have some information, and then they start propagating the information along the edges, and you want the information to be propagated as efficiently, as quick as possible. And okay, there are two constraints. And we will see that these constraints are antagonists. There is a tension between them. The first constraint is that every set of vertices should be well connected to the remaining vertices. This means to the complement, to ensure quick transmission of information. And the second constraint is that the number of edges should not be too large. Because edges, I mean, if you think in the past, the communication lines were made of copper wires. Nowadays, they are made of optical fibers, but you have to pay for that. So because you must pay for the copper or optical fibers used. And there is a tension in between. And let me be more concrete. What is the... Yeah, but precisely, what is the best graph by that respect? It's the so-called complete graph, where you have your nodes, you have your vertices, and you put a y, you put an edge between any two of them. So the best graph regarding the first constraint is the complete graph. K sub n. So if okay, here's drawing of K5. So that's K5, and you see that the number of edges here is n minus 1 over 2, so n choose 2, and well, what you observe is that this is quadratic in n. So this means that this quickly becomes expensive. And so a consequence in the modelization is that we stick to regular graphs. So remember, a graph is K regular if every vertex has exactly K neighbors. So this means it's connected to K other vertices. So K is some fixed number. And in this case, you have a formula to compute the number of edges. You see, from each vertex, you see K edge. So that gives you K times V. But each edge has been seen twice. So you divide by 2. And so, but what this shows is that if we stick to K regular graphs, the number of edges will be linear in the number of vertices. So it will be much better than complete graphs. Okay. And finally, before I go into rigorous definitions, one requirement is that we want to use finite graphs to model large communication circuits, but we don't want a single graph. We want to model a graph, a system which can be arbitrarily large. So we are not after one graph, we are after a family of graphs. To model systems which can be arbitrarily large, we look for a family of finite graphs with size, with number of vertices going to a plus infinity. So graphs which are larger and larger. Because I'm saying this because when we talk about expander graphs, some people, well, sometimes people think that we are talking about a given finite graph. But actually, you will see that the definition makes sense not for one graph, but for a family. So it's quite important to consider not one graph, but an infinite family of graphs. Well, infinite countable, of course. And now, let me make precise sense of the first requirement. So, to measure connectivity of X, suppose that A is a subset of the vertex set. And we define the boundary of A del A. This will be the set of edges connecting A to its complement. So E connects A to V minus A. So these are the set of edges with 1 foot in A and 1 foot in V minus A. So the mental image that I have is something, so here is the graph X, here is A, and I'm looking at edges which do like that. So for each of them, there is one vertex in A and one vertex outside of A. So that will be del A. And okay, I still have a few minutes. So observe that the boundary of A, or the boundary of the complement of A, is the same, because this definition is symmetric in passing to the complement. So as a consequence, we may restrict to subsets A, which are at most the half of the total number of vertices. So that the number of vertices of A is at most n over 2, where n is the total number of vertices. And now with this, I may define what is called the isoperimetric constant. Well, actually, there are several names. Some people call it the isoperimetric constant. I tend to follow that tradition. And some people call it the Cheeger constant. Of X. So this is h of X. So that will be the minimum of the ratio between the boundary of A and A, taken over subsets A, which are at most half of the total number, and to avoid zeros over 0, you also require that A is non-empty. And so, and this is really something which, this is considered as a measure of the quality of X as a transmitter of information. Because if it's big, this means that for all sets of vertices, there are relatively a large number of edges connecting A to V minus A. So this is viewed as measuring the quality of X as communication system. The bigger Hx, the better X. And now, with this, I can define what is a family of expanders. So let Xn be a family of K-regular finite connected graphs. So it is a family of expanders if, well, first, these graphs are larger and larger, so this means that the number of their vertices tends to infinity, and the important condition is the following, that the isoperimetric constant is bounded below by a non-zero constant. So there exists a positive epsilon such that h of xn is at least epsilon for every n. So this is considered, well, assuming such families exist, they are viewed as solutions to the modeling problem which I explained at the beginning of the chapter. So they are, because they have a fairly large isoperimetric constant, they are viewed as good communication systems. The number of edges is certainly linear in the number of vertices because of K regularity, and finally they can be taken arbitrarily large. And now it's by no means obvious that these things exist. Oh, let me give you first a non-example. Well, an example of a family which is not an expanding family. So if you take K equals 2, well, what is a finite 2 regular graph? It's a cycle. And the family of cycles Cn is not an expander family, and that's obvious. Because, okay, here's a cycle Cn, and now what you do is take a half cycle. And the boundary will have exactly 2 elements. So for a half cycle, A, the boundary of A has exactly 2 edges. So one here, one there. And this means that the isoperimetric constant is of the order of 1 over n. Okay, so maybe it's a good point to have a break, 10 minutes like yesterday. So we are left with the question, do these objects exist, families of expanders? And the positive answer was first given by Pinsker. So he is a theoretical computer scientist And I think that was 1969, something like that. So, okay. One way to phrase the result is that most graphs are good. And to be more precise, what he proved was the following. So take k, which is at least 3, and for any positive epsilon, the proportion of k-regular graphs x on n vertices, on n vertices, such that h of xn is less than epsilon. So if you fix, k is fixed once and for all. So if you fix n, of course, you have finitely many k-regular graphs on n vertices, and so you may count them. And among those, you look at those which are bad in the sense that they have small isoperimetric constant, and you look at the ratio, and so what I call the proportion. And this proportion tends to 0 for n going to infinity. And as a consequence, expander graphs do exist, but it's a purely existential result. Namely, we have existence without constructing any. It's a little bit like when we say that there are transcendental numbers because the field of algebraic numbers is countable. And we haven't shown any transcendental number. So philosophically, we are in the same situation. And the first, and of course, this is no good at all for a computer scientist. Right? They really want explicit examples, and the first explicit examples were provided by Margulis in 1973, and using property T. So you must know that in the good old times of USSR, Margulis was working in an institute for communication theory. So that was. So what is Margulis construction? Well, we're going to do a bit of so-called algebraic graph theory. So if x, which is VE, is finite, connected, k-regular graph, we have an operator which is called the Laplace operator. And so the Laplace operator, delta, so it's an operator which acts on L2 of V. Oh yeah, L2 of V is a baby Hilbert space. It's a finite dimensional Hilbert space. But anyway, so here we are really doing linear algebra. And the formula is that, so you take a function f on vertices, and when you define a new function with delta of f at x, this will be k times f of x minus the sum over vertices which are adjacent. So this tilde means that y is a neighbor of x. So that's the adjacency. So y is a neighbor of x, sorry, of f of y. And, well, for instance, when we in the first course, or either on complex analysis or in potential theory, we learn a bit about harmonic functions, and we learn about the mean principle, that a function is harmonic if and only if it's equal to its mean on small circles. Well, here basically it's in the definition. A function is harmonic if and only if the value of at x is the mean of the values on the neighbors. And this turns out to be a non-negative operator with eigenvalues. Well, the first is 0, because if you plug a constant function, well, constant functions are harmonic. And because of connectedness, they are the only ones. So if you have a function in the kernel here, well, suppose that it's a real valued function. Take a vertex where the value is maximum. And then you see that because of the mean value, this maximum is also attained on the vertices. And then you extend little by little, you prove that your function is constant. So zero is an eigenvalue of multiplicity 1. What will be important for us is that guy, lambda 1, the first non-zero eigenvalue. And then there are the others, lambda 2, lambda 3, etc., up to lambda n minus 1. N being the total number of vertices. Now, why is this operator positive? Well, suppose we orient the edges. So this means that for every edge, E, we put an arrow which allows us to define the original, the origin, E minus, and the terminus, E plus. So we orient the edges, and then we may define the co-boundary operator. Co-boundary operator, that's an operator from functions on vertices to functions on edges. Takes the function f, and df at an edge E is f of E plus minus f of E minus. So it's discrete differentiation in the or finite difference in the direction of the edge. Then you have the transpose operator d star that goes in the opposite direction. And when you compute d star xi, so here xi is a function on edges. I was tempted to say a one form. So d star xi at say x, this will be the sum over edges E, such that E plus is x of xi of E minus the sum over edges such that E minus is x of xi of E. And I leave you as an exercise using these two formulas that to check that the Laplace operator is d star d as every Riemannian geometer is known. No. but okay, but it's a two-line computation. But this is interesting for us for the following reason, that if we express lambda 1 by, oh yeah, before, also, this shows, to define D, we had to choose an orientation. To define delta, we hadn't. So this means that D and D star depends on the choice of orientation, but D star D does not. Okay, so that was just a small digression. Now, by the Rayleigh principle, we have, let's say, a variational principle for lambda 1, which tells us that lambda 1 is the infimum of the ratio between, well, the quadratic form associated with the Laplace operator, so Laplace of f scalar with f divided by the norm of f squared, taken over f in L2 of v, orthogonal to the kernel, so orthogonal to the constant function 1. And using that delta is d star d, this is the same thing as the infimum of df squared divided by f squared for f in L2 of v, f orthogonal to 1. Okay? So, okay. So sometimes this is called the Dirichlet norm, L2 norm, but I don't want to go into that. And now let me prove a lemma, which is that lambda 1 is less or equal to twice the isoperimetric constant. There is another inequality from above which shows that lambda 1, which is really an algebraic quantity, and h, which is a combinatorial quantity, they do measure, let's say, equivalent things. This double inequality is called the Chigger-Boozer inequality because neither Chigger nor Boozer worked on that. But they are called Chigger-Boozer for, let's say, a good reason, which is that it's a discrete analog of an inequality on lambda 1 of a closed Riemannian manifold, and which was proved, well, one of them was proved by Chigger and the other one was proved by Boozer. And so you may define the isoperimetric constant of a closed manifold if you compare the boundary I mean the Riemannian area of the boundary of a domain to the volume of the domain. So you can write down a very similar quantity, except that you have to be careful with smoothness of your domain, because you need to take a domain with a smooth boundary, etc., etc. I mean, it's far easier in the discrete setting, and lambda 1, and on the other end, of course, you have the Riemannian Laplace operator, and which it's well known that the spectrum is discrete, and you take the first non-zero eigenvalue, and so okay, as I said, to summarize, this is 1/2 of the Chigger-Boozer inequality. Okay, so let me prove this inequality. So, start with a subset V. So remember that h of x is a minimum over subsets of V. So, well, we take a subset which realizes h of x. So let A in V such that, okay, so A is at most, cardinality of A is at most n over 2, and we assume that h of x is cardinality of the boundary divided by cardinality of A. Now, we define the function psi of A on the vertex set on V by the following recipe. If x is a vertex in A, we put as value number of vertices in the complement. And if x is a vertex not in A, we put as value minus cardinality of A. And we do that to ensure that psi sub A is orthogonal to 1. Indeed, if you sum all the values over vertices, you find 0. So sum over x in V of psi of A x is 0, and this means that psi of A is orthogonal to 1. So I can use it as a test function for lambda 1. So I will need its L2 norm squared. So let's compute. So it's V minus A squared times, how many times? Well, cardinal of A times, plus A squared, how many times? V minus 1. V minus A, sorry. And, okay, so that's A, V minus A, times A plus V minus A, that's N. More interesting, what is the coboundary of that function? Well, you see that function is constant on A, it's constant on the complement. So what are the edges which will contribute to d psi A are exactly the edges on the boundary of A. So if we evaluate at an edge of E, it will be 0 if E is not in the boundary of A. And if E is in the boundary of A, it will be the difference between these two quantities, namely n, up to sign. So it's plus or minus n. But since we are going to square it, the plus or minus doesn't matter at all. So what we need is the L2 norm, and we see that this is n squared times the cardinality of the A. And now, if we form the Rayleigh quotient, we have that lambda 1 is less than d psi A squared divided by psi A squared. So we have everything, so that n squared divided by dA, and here n A V minus A. But remember that cardinality of A is less than n over 2. So so this means that cardinality of V minus A is larger than n over 2. And using that, you estimate this by twice boundary of A divided by A. And this is exactly twice h of x. And the proof. Okay. So, as I told you, Margulis used property T, so this means he used groups. And how can you return groups into graphs? Well, by using the Cayley graph construction. So let G be a finitely generated group, and let S be a finite symmetric. Symmetric means that S is stable under passing to the inverse. Symmetric generating set of G. The Cayley graph script G, GF is the graph such that, well, the vertex set is G, so the group itself, and the edge set is a set of pairs of the form G, SG, where G is a group element and S is a generator. So this means that to move away from a vertex G, you left multiply by all generators. And observe that this is a symmetric relation because precisely my set has been chosen to be symmetric. And okay, we get a graph which is K regular for K being the cardinality of S, and which is connected because S is generating. So for instance, if we start from the identity of the group, well, using this procedure of flash multiplication, we will be able to reach any element. So it's connected. And also this graph is vertex transitive because to define it, we used left multiplications. So the group is still acting on the right by right multiplication, and it acts by preserving that adjacency, and it acts transitively. So G acts transitively on V by right multiplication. So, if G, okay, so far I'm assuming that the G is finitely generated. It doesn't need to be finite. But if moreover G is finite, well, what is the Laplace operator? What does it do? Well, Laplace operator at G is cardinality of S times f of G minus sum over generators of f of SG, because vertices of G are on the form SG. But here, we recognize the left regular representation of our group G. So this is the same as cardinality of S, f of G, minus sum over S, lambda S f at G. So there is, well, when you get rid of the function, this formula takes especially a simple form. The Laplace operator is S time the identity minus the sum of over lambda S taken over the J-ring set. Lambda is the left regular representation. Of G on L2 of G. So yeah, maybe yesterday I denoted by lambda sum G. Yeah, probably I denoted by. So remember how it goes. Lambda G, let's say S F evaluated at G. This is F of S inverse G. So this is the representation associated with the action by left translations. And now here is Margulis' theorem. Okay. Let G be a discrete group with property T, and assume that G is okay. The idea is really to do a construction from above. Namely, we start from an infinite group, and this should be be an infinite discrete group with property T. And we are going to take quotients, and the expanders will be killigraphs of finite quotients. But we need an assumption that guarantees the existence of many finite quotients, and this condition is called in group theory residual finiteness. So we assume that G is residually finite. And this means the following. There exists a decreasing sequence and capital N sub n of finite index normal subgroups of G such that the intersection of all these normal subgroups is reduced to the identity. So residually finite alludes to the following thing, that if you have a non-identity element in G, you will find a finite quotient which witnesses the non-triviality of this element. Indeed, you can take this normal subgroup to be deep enough to miss your element, then in the quotient your element will survive. And okay, yeah, this is not pedagogical, but let me give an example. So the example is not part of the theorem, sorry about that. But take as the mother group, so the group above, SLDZ, where D is at least 3 in order to have property T. And then you have reduction. You can take reduction modulo n. So you have a map from SLDZ onto SLD of the finite ring Z mod n Z, Z mod n Z. So that's reduction modulo n. And the corresponding normal subgroup will be the kernel of this reduction. It's also called the congruence subgroup. And yeah, and this exhibits. The idea is very simple. That if you have a non-identity element in a cell DZ, if you take n much larger than all the coefficients, you will see the same matrix in the quotient. So. Okay, now what is the statement of Margoulet's theorem? Take S, a finite symmetric generating subset of G, then the family of Cayley graphs so you take the quotient group, which is a finite group, but here there is a caveat, which is that you need to take the generating set which comes from above. You take the image of S in the quotient. But anyway, you know that it generates, so it gives you a Cayley graph, and the theorem is that this family of Cayley graph is a family of S regular expanders. The question what's happened if instead of, in some sense this means you take a unique generating set, which lies in the mother group. And the question about what happens if for every n you take a different generating set, provided that they all have the same cardinality. Do you still get an expander family? This question is extremely difficult, but in the same time, there has been amazing recent progress due to people around Jean Bourgain in Princeton. So there's the so-called sum product phenomenon. So the Bourgain, Sarnak has been involved, and lots of bright young people. But anyway, but this is not related anymore to, this recent work is not related anymore to property T. So to stick to my subject, well, let me prove that. Okay. By property T for the group G, we know that if pi is a unitary representation of G without non-zero fixed vectors, oh, sorry. No, I'm messing up the quantifiers. So there exists a positive epsilon such that if pi is a representation of G without non-zero fixed vectors, so if there are, by property T, if there are no fixed vectors, there are no approximate fixed vectors. So this means that for every psi in the Hilbert space of norm 1, the maximum over S in a compact set, for instance in the generating set, of pi of S psi minus psi, this will be at least epsilon. And in passing, the best possible epsilon is called the Kazhdan constant. For the pair GS. But okay, this is not important for the proof. So what is important is that we have this epsilon. So this tells us that whenever we have a representation without fixed vectors, for every unit vector, we can find at least one generator which moves it by at least epsilon. No? Let me denote by L2 sub 0 of G mod Nn the orthogonal of 1 in L2 of the quotient. So this is the same thing as the functions which sum up to 0. So these are functions in L2 of G and N, mod Nn, such that the sum over x in the quotient of f of x is 0. And we have the left regular representation of the quotient group, which acts on that Hilbert space, but it preserves that hyperplane. So that it's an hyperplane invariant under lambda of G mod Nn. Yeah. And so let pi sub n be the representation of G on that hyperplane L2 of G mod Nn, L2 0 of G mod Nn, obtained by composing the left regular representation of the quotient with the quotient map. From G to that quotient. Okay. And pi sub n is a representation of G without non-zero fixed vectors, because the fixed vectors in L2 of G mod Nn are exactly the constant, and we killed the constant by taking the orthogonal. So pi sub n has no non-zero fixed vector, meaning that if I take f in L2 0 of G mod NN, let's say I can assume that the L2 norm is 1. Well, there will be at least one generator, let's say S0 in F, such that pi of S0 F minus F will be greater or equal to epsilon. So now, if I square this, this will tell me that the 2 minus twice the real part of pi S0 F, scalar product with F, is larger than epsilon over 2. And rearranging 1 minus epsilon square over 2 is larger than the real part of pi S0 F F. And I suppose that pi should be pi sub n everywhere. Yeah. Pi sub n. Okay. And now with this, we are going to bound lambda 1 of that Cayley graph by a non-zero constant. You know, well, there is a rather posh way of phrasing this, which is to say that there is a uniform spectral gap. So the lambda 1 is bounded below by a constant which only depends on the group and the generating set. Actually, it depends on the so-called Kazhdan constant. That's the reason for introducing this definition, actually. But so let us do that. So remember that the Laplace operator is S time identity minus sum over S in S pi sub n S. So here I'm using the fact that all of my Cayley graphs come from this generating set from above. And now, let me apply this to this function f, which is of norm 1. So here I will have cardinality of S of minus sum over generators, pi of n S f in F. On the left-hand side, the result is real. It's a non-negative number. So I can put the real part all over. So this is S minus. And here, in this sum, I will separate the term corresponding to S0. So here I will sum over S distinct from S0, real part of pi of S F minus F. And then I still have the term corresponding to S0, real part of pi of S0 F F. And at this point, I always make a little prayer to say, I hope there is no sign mistake, because we have to estimate things with negative signs. But I think this will, but I repeat it before coming, so this should be okay. So this will be greater than S minus. Okay. Here, every of the term here just by Cauchy-Schwarz, is less or equal to 1. How many of them? Cardinality of S minus 1. So here I will have S, cardinality of S minus 1. And the final term is less or equal to 1 minus epsilon square over 2. And I think that when the dust settles, you get exactly epsilon square over 2. Question? Oh, because this is a real number. It's not negative. Yeah. So okay. So I'm allowed to take real part all over. Anyway, so yeah, and again by the Rayleigh principle, this implies that lambda 1 is larger than epsilon square over 2, and therefore H by so by the Chigger-Boozer inequality, H of this Kelly graph is larger than, should be epsilon square over 4. That's it. Okay, let me close that by mentioning that computing the exact value of a constant is something extremely difficult. And I mean, if you look at for instance, at SLDZ, it is generated by elementary matrices. So I can elementary matrices with ones on the diagonal and exactly 1 plus 1 outside diagonal. So there is this canonical set of I guess DD minus 1 matrices, and there is a Bulgarian mathematician, Kasabov, which in 2005 has, so he estimated the Kazhdan constant from above and from below. So the exact value seems out of reach. So we have to content ourselves with estimates. But what is nice with Kasabov is that his estimates is asymptotically sharp in D. Namely that when D goes to infinity, I mean, this converges to a single value, and the answer is that the Kazhdan constant is of the order of 1 over root D, if I remember correctly. But in general, it's for finite groups. That's a cute exercise for let's say for a master thesis for a student who has been through a course in representation theory of finite groups. You give him or her his or her favorite finite group, his or her favorite generating set, and try to compute. And this is really cute. There are nice computations to be done. But as soon as you go to infinite groups with property T, this is, I mean, if he or she can do it, this will be published in an excellent journal. Okay, I'll thank you for your attention. Yeah, no, the point is that, you see, every lattice in a simple Lie group is residually finite by Malchev's theorem. And so, okay, this result of Margulis says, okay, take any lattice with property T and then take the finite quotient and get the Kelly graph. Thank you.